So it's a pleasure to be here, and then soon I'll be physically there as well in Barcelona. So I'm very happy about that. Yeah, so we're gonna talk about exotic mesons, and then as Arnaud say, how to analyze data from experimental collaboration. So first of all, I introduce my colleagues. So because some of the work that's going to be presented here have been made in collaboration with all these gentlemen and Astrid as well. So the most of them are based either in Indiana or Jefferson Lab, because the Joint Physics Analysis Center was initially created with Indiana University and Jefferson Lab. So most of us have either been postdoc in one of these two universities, and then we move on to other positions. All right. So we're going to talk about hadrons. So hadrons is everything related to the strong forces, like the force that binds quarks into proton, neutron that you can find in nuclei. And the quarks are bound by gluon, as you know. So according to the quark model and then the theory, which is called the quantum chromodynamics, quarks can bind in by triplets to form baryons like matter like protons and neutrons, or excited baryons that decay quickly into protons and neutrons and another particle. Quarks can also arrange in pair, like a quark and an antiquark, to form mesons. And those are called ordinary hadrons. They are well-known particles discovered since the last 50 years. And we know that we have 6 types of quarks that can form all these ordinary baryons and mesons. Now, beside these 2 standard configurations, which is 3 quarks or a quark and an antiquark pair, the QCD predicts that other kind of resonances could be formed, other type of quark configuration. So you can have like a quark-antiquark pair in which the gluon field is in the excited state, or equivalently that the gluon is like an effective gluons that carries quantum numbers. You can have like multi-quark configuration like tetraquarks and pentaquark, or you can even have like no quark at all in the valence. Like it would be like a glue ball, a pure state of gluons. There are a lot of candidates nowadays found by several experiments related to tetraquark and pentaquark, especially in the heavy sector. They are usually called by the name XYZ, just to emphasize that we don't know exactly what they are. But this is not what I will present today. I will focus more on the hybrid mesons part. So the hybrid mesons has the advantage that, as we're going to see, that can be easily observed thanks to its quantum numbers. And first of all, yeah, so all this is really like finding or interpret like signal or resonances is really like a work of collaborative works between experimentalists and theorists or phenomenologists. So of course, experimentalists, they design, they build the detector, they collect data. But apart from that, of course, there are works needed from theorists, like to develop models, like to make some pure prediction of what we should see in the experiment. But also there are some theoretical work, as we're going to see, just to develop technique to analyze data, like how to, from the raw data, build observables that are meaningful, and how to analyze data. So this is really typically a joint collaboration between phenomenologists and experimentalists. And then, of course, once we have analyzed data, then we can compare that with some theory prediction, as I said, by constituent model or lattice QCD, and then merging all this knowledge to have like a clear picture or an interpretation of what would be the signal, what kind of quark content this resonance would be. So tetraquark, as I said, tetraquark and sometimes pentaquark, they can have like, or glue balls, they can have quantum numbers. They can have any quantum numbers, but the hybrid mesons, because of its additional gluons, can have more quantum numbers. So in particular, if you take like just a quark and anti-quark pair, just by the quantum number, because the spin, the total spin of the quark can be, the sum of the two can be only 0 or 1, then the quantum number are only restricted. Angular momentum is an integer as well. So if you have only a quark and an anti-quark pair, you can only form the quantum number GPC that are in blue. Now, if you have an addition, if the gluon field is in an excited state, or if the gluon carry the quantum number, which is equivalent, you can actually form the missing quantum numbers. Of course, exotic meson can have like regular quantum numbers, but then they would mix with regular quark, and then that would be more difficult to observe. The important thing is that you can have, like, for instance, the 1 minus plus quantum numbers, and it is believed, according to many models and lattice calculation, that the lightest one would be the 1 minus plus. So this is important because that means that if we see a signal, like a resonance, in a wave that has quantum number 1 minus plus, we know that it's not, it cannot be a regular meson, an ordinary meson. So that's a big advantage concerning the interpretation of a resonance for a hybrid meson, because they have like quantum numbers, selective quantum numbers. So the lightest one is 1 minus plus. So so we need to observe that. So we need to identify like a final state. And then one of the main channel of disintegration would be simply to have disintegration in two pseudoscalar, like because the pi1 here, the quantum number pi means it's an isovector. So it decays into an isovector and an isoscalar, the pion and the eta. And then if you place those two in a p wave, then you can form this quantum number 1 minus plus. So eta pi in a p wave, or in general in an odd wave, would create exotic quantum number. So p wave would be this, L equals 3 would be this one. So that's why there are several experiments, in particular COMPASS at CERN and GlueX at Jefferson Lab, whose experimental program involve resolving the eta pi final state, analyzing that and then perhaps found exotic mesons there. So talking about facilities, so we're going to talk about COMPASS and GlueX. So COMPASS is at CERN here in Switzerland. GlueX is part of the Jefferson Lab, so here in Virginia. There's also CLASS, which is a twin experiment. GlueX works with a real photon beam, polarized photon beam. CLASS works with the electron beam. So we have an electron beam at Jefferson Lab. And then for all D, where there is GlueX, there is a crystal so the electron goes through a crystal and then just X-ray, so real photon. Where for the other hole, like CLASS in hole B, it's just pure electron scattering on a hydrogen target, so basically proton. There's also another important facility in China at BESS, more related to XYZ, like heavy quark production. I won't talk about that today. Right, so
Vincent, can
yes.
I ask you something?
Yes, of course, yes.
So just a very basic question. So these exotic mesons,
yes,
that the fact that they would exist, is it a prediction of the theory? And is it expected that they are found in the experiment? Or is it not clear from the theoretical point of view? Or what's the
so there are 2 points here. So the first is that they can exist from QCD, it's allowed. So you know that, physics is like a democracy. No? If it's not explicitly prohibited, then it should appear, right? But so in principle, they exist. Now, there might be some, for some reason, they might decouple or be very weakly produced or just decouple from ordinary matter. But we do have evidence from model that they can do bind and then have like a relatively low mass, like 1.5, 1.6 GeV, and then measurable decay. And this is also supported by lattice QCD prediction. So I don't have the plot, but there's a recent paper, like I believe like from a month or two ago, by my colleague in Jefferson Lab and in the UK, the Hadron Spectrum Collaboration. So where they have, it's an unphysical pion mass, but you see they do scattering. So they can do, instead of having like a pion beam that you shoot on a hydrogen target, they can do somehow like elastic eta pi scattering somehow. I mean, and then they do find also odd wave. And then they do find resonance in odd wave. So everything points towards the existence of those guys, yes.
I see. So yeah, if I understand correctly, so this is like a prediction of the theory or the best calculations we have so far. And if for some reason these states are not found in the experiments, it means something is not completely well understood, right?
Exactly, exactly.
Okay, thanks.
Yeah. So COMPASS has accumulated data over the last 2 decades, especially in the eta pi and the eta prime pi channel. So the eta is not stable, but you can reconstruct that with this decay into 2 photon of 3 pion. And then as you can here, so there are different variables. Like the total energy is fixed and is very high at COMPASS. So the 190 energy beam pion is very energetic, so it doesn't really have the time to be absorbed by the target. So it basically, it's a diffractive process when it fragments into, in this case, into a eta and a pion. So because the energy is so high, we don't have to worry about the beam being absorbed by the proton and forming resonances like the delta or the n star or the resonances. That will be more a problem for GluX, as we can see. So the energy is fixed. The momentum transfer here is typically very low and it's integrating over. So the remaining variable is really the mass of the subsystem, like you can see, like from threshold to about like 4 or 5 GeV. And then of course, it's these two particles, I mean, there's a relative angle. So there's a theta and a phi, there's a polar and azimuthal angle. So if you integrate over this angle and then plot the spectrum with respect to the invariant mass, then this is what you obtain. So we see here a clear peak that later we will see will be associated by a D wave. So if we actually do not integrate over one angle, so the polar angle, but do integrate over the azimuthal one, then we obtain this scatter plot when every point here represents one event. And then for this peak here represents this one. So here we see that we can see that we have a D wave because we have like the 0 of the sine and then the 0 of the cos. So it's like a sine, it's a cos times a sine, everything square. So this we see that this peak here, because of its angular distribution, it's a D wave. So the angular distribution tells us about the quantum numbers. And in this case, a D wave would be quantum number 2++. So, and then the name for that is A2. And this is for eta pi. Now for eta prime pi, the scatter plot is a little bit messier. But there are also one thing which is very important is that we're going to see also in detail is the asymmetry between forward and backward here. So this asymmetry, as we can see, is really related to the presence of odd wave. That means that the presence of exotic wave. So here, just by seeing that there is a bigger asymmetry in eta prime, we see that here there's much less even than here. So we can anticipate that when we're going to study the angular distribution of this, we expect to have like more odd wave, so the more exotic wave. So as I said, to know the quantum number of the system, you need to inspect the angular dependence, so expanding this into spherical harmonic. And this is what the COMPASS collaboration has done. And in this case, for this, with a pion beam, there's not too much difficulties. The Compass collaboration has performed that. It's and it's been into mass of the eta pi system. And here you can see the P wave, the D wave, and then the G wave at the L equal 4. The black is eta prime, and then the red is eta, and it's scaled to compensate from the phase space. So we see that in the even wave, L equal 2 and equal 4, the eta and the eta prime, they really have very similar waves. Where for the odd wave, the exotic one, we can see a much stronger dominance of an exotic wave. So the question is, I mean, whether here there is like a resonance or not. So here we know that there's probably like the A2, which is a well-known resonance. Here, the A4 around 2 Jeff here, so regular mesons. And then the question is, where here do we actually see an exotic meson? So of course, so the question is now, what is actually a resonance? What's the definition of a resonance? How we find that? So here the energy is taken and then the invariant mass is real, but we can show that one of the principle of in particle physics is that the function that describes the process, of course, even though that the eta pi mass is a real number, you measure it in the real number, can be treated as a complex variable. And actually the analytic structure of this function for the mass here, S is the mass square of the system, eta pi mass. The analytic structure of the function do matter. So because of conservation of probability, which is also called unitarity, we know that the function is discontinuous along the real axis. So the data are on for real axis, but strictly speaking is real plus 1 epsilon. It's really like on this edge of this function. And unitarity tells us what's the gap here. So, and this is very important because this allows us to also to parameterize that. So the idea is that, of course, if you have an analytic function, you can use all the known theorem for complex functions that are very powerful. And we know that every time we see like some kind of structure in an analytic function, it comes from a singularity, pole or a cut. A function that does not have pole or cut can only be a constant. There's no any structure that can be seen. So here the thing is that we see like some enhancement. And actually, if we actually make a smooth continuation, means if we go to the second Riemann sheet here, then unitarity tells us that there will be poles. And then those poles are responsible for this structure that we see on the real axis. And these are the poles that we call resonances. So we can also show that these poles, they are universal in the sense that because of unitarity, conservation of probability, if it appears in one channel, it should appear, the same pole should appear in all the other channels that have the same quantum numbers. Of course, the residue of the pole may be weak or null, but the pole should be there. So really when we hunt for properties of exotic mesons or resonance in general, we look for pole in the second Riemann sheet. So yeah, so unitarity tells us that there will be pole. So an example here, then we have like the A2 here that's parameterized. And then on this shoulder here on 1.7, here this shoulder actually found that there was also a radial excitation of this guy, another pole here. So we have the compass data, and then we design a model that satisfies all this S-matrix constraint like unitarity and causality and analyticity. So it's a K-matrix fit for the coupled channel eta pi and eta prime pi. Of course, the waves are independent, except that compass also measures the interference, so the phase difference between P and D wave. So because of that, then of course, this constrains the S and the P wave together. Otherwise, they would be independent. So the important thing is that before we did that analysis, I mean, and before COMPAS arrived in the 90s, there were also experiments separately in eta pi and eta prime pi. And then as you can see, the enhancement in the P wave does not appear in the same place. So here you see an enhancement around roughly at 1400, where here the enhancement is at 1600. So there were like some naive parameterization by experimentalists that do not include all the analytics, the proper analytic structure of the partial wave, and basically would fit that with and arguing that the position of the pole or the mesons would be really like the peak that we observe. So in the PDG now, you can see that there's two entries, that the 1400 and the 1600. And then the reason behind that is that there were two independent fit, just fitting with simple Brake-Wigner to these two channels. So we did a combined fit and we found only one pole, which is close actually to the 1600. So in green here is a combined fit that you can see. And in the complex number, so this is the second Riemann sheet, which we have the width here, or the imaginary part, and then the mass here. We saw, of course, the A2, and then you see, because the A2 was very narrow, so narrow that its position is well known, known very precisely. There was also this A2 prime, as I mentioned, and then we found only one pole here, the pi one, which is still suffers from significant uncertainty, and then all the other ellipses is like some systematic. So all the ellipses were changed in the model, where the green and the yellow are like statistical error. So we found only one pole, fairly well constrained with the data. Now the question is that, so we can actually understand more where it comes, like its origin, and also constrain this parameterization more. So far, what we've done with COMPAS is really studying the below 2 GeV regions, like the resonance region, and then the exotic mesons around 1.6 here, and here. But I told you that actually, if there were only even wave, the plot would be totally symmetric in cosine. So the fact that there's a small asymmetry here that is more visible in the tail implies that they are odd wave, and they are the odd wave exotic. So somehow the fact that the dissymmetry in these tails tell us about the origin of exotic waves. So we would like to understand that. And now the question was the physics behind this high energy. So here we have like the pion mass, the pion beam, sorry, is at high energy. And now we consider like the two decay product to be also as well at high mass. So it's somehow like also those two, they also interact diffractively. So you see that there is one diffraction by the Pomeron because the beam is high. But now if we look at the high invariant mass of this eta pi, then they also interact diffractively. So or via Regge exchanges, if you want. So if we are at the very forward, it means that the eta, the angles are the angles of the eta. So the very forward means that the eta is going very forward along the beam, where in the backward region is the opposite. It's really like the pion is going forward. Now you can see that because the eta and the pion, they have different quantum numbers, there will be different quantum number for this force between, between the beam and the fast particle. So if you imagine that if you have like a SU3 world, where the strange quark has the same mass of the light quark, then you have like an octet. And if you consider that the eta would be like the octet, in that case, would be basically the isoscalar partner of the pi, meaning that all its couplings, all its mass would be exactly the same as the pion, then this diagram with the top A2 would be the same diagram of this F2. It's called exchange degeneracy. So in that case, these two diagrams, they would be totally symmetric. And I'm forgetting this one. So one of the suspicion would be that the dissymmetry would be related by this extra Pomerons. as I said, because in the SU3 limit, those two diagrams here, F2 and A2, would be the same. Actually, we found that it was not the case. So it's also interesting to see that in this picture, why maybe the eta prime would be more dissymmetric. So you know that the eta prime acquire higher mass than the eta because of the axial anomaly, and this is something related to the gluonic to the gluon field in the QCD Lagrangian. So the Pomerant can also be related to gluon field. So we expected that the dissymmetry would be more pronounced in eta prime because it would couple more to Pomerant, that is to gluons, than the eta itself. And then that, because of this enhancement of the Pomerant, that would create a dissymmetry, and then this dissymmetry would propagate in the low energy region and then create like a node wave that would be like the exotic mesons. So this, I'm going to show you all this is in preliminary result, but apparently we found that surprisingly would maybe not be the case. Yeah, so I said that we can actually formulate, so there's a relation between the diffractive region and then the low energy region. You can actually formulate that mathematically using dispersion relation. So by using like Cauchy theorem, you can make sense and then say that the average, that means certain integral of up to a cutoff of the low energy region needs to be equal to the diffractive part. So this is, so for instance, the way we can illustrate that is using just simple pion nucleon elastic scattering. So at low energy, you can produce the delta peak that you can see here. This is the imaginary part of the amplitude. This is basically the total cross section up to the phase space. So you can see the delta peak here, you have all the resonance. But once you enter the high energy regime, then the cross section is really smooth. And what the sum rule says is that if you extrapolate the smooth part down to threshold, you see that on average, it equals the resonance, if you do the integral. So you can formulate that. And then the goal is that once you have the data here, you can actually constrain your fit to the partial wave here in the low energy region using these sum rules and a fit to the high energy region. So the first step is, as I said, to fit the resonance region. And then the second step is to fit the diffractive region that we've been doing. And we actually found that it was much more complicated than expected. So we've been doing that since more than a year now. So I'm going to show you preliminary result with writing the paper now. And then eventually we need to relate these two by the sum rule. So we need to write down the sum rule using the property of dispersion relation, and then do a global fit where instead of fitting only the low energy part, then doing really a complete fit of the whole spectrum constrained by the sum rule. So in the fit, we realized there are several features that surprised us. Like for instance, if we were considering only Pomerant, so the bottom exchange here, you know that it has the quantum number of the vacuum. So typically you have Pomerant, but in addition to the Pomerant, you can always have the F2, which is the same quantum number of the Pomerant. So surprisingly, we found that if we were doing a fit with only Pomerant in the bottom, which has different parameters than the F2, we found that in the forward region, so this is just the event sum, but only in the forward region, so fast eta, the fit in yellow with only Pomerant was in agreement with the mass slope that we found, but it was not the case in the backward region. In the backward region, then we did a fit when we were considering only the F2 exchange, so no Pomerant, this is the blue fit. Then we found the opposite situation, that apparently in the backward region, the data, for whatever reason, prefer the bottom exchange to be the F2. So this is something that we were not expecting. Again, so at the end, now we did a combined fit, and then we see that indeed, so this number, I told you that the two yellow and the two blue, we expected to be to be of the same magnitude because of the degeneracy in the SU3 limit, we see that the two yellow, 28 here, 20, they are relatively close. So they are only so they are probably not responsible for the asymmetry forward, backward. But this one, actually the numbers are quite different. So surprisingly, it was not, I mean, the bottom Pomeron in the bottom that was responsible for the asymmetry, but it was more like the bottom F2 we changed. And we did, yeah, so this is example of the fit. So here it's represented when we actually slice at fixed mass. So here you have like the scatter plot. You imagine that you do like at fixed mass, so like the mass is written on the top. So 2.52 would be the slice in blue, more or less. And you can see an asymmetry between backward and forward. And in yellow is the data, and then in black is the model. Yeah, so this is, so we discussed that the result for the eta, and we can see how it compares with eta prime. So in eta prime, we don't have yet the error. The error is performed by a bootstrap that actually Cesar is running on this cluster in Mexico, because these are quite intense in calculation. Doing a nominal fit, you can do that on a laptop, but really doing like thousands and thousands of fits, we run that on a cluster. And then the same thing happened in eta prime, in the sense that the yellow diagram with bottom Pomeron are fairly equal, but then the asymmetry, surprisingly, is really related to the bottom F2. So this is still something we need to understand. So we are working on like trying to have like a theoretical evaluation of every independent contribution to see if there is a mismatch between the theoretical evaluation, the expectation, and then the phenomenological, empirical result of the fit. Yeah. So, and then as I said, so lastly, what we have to do like next is really to combine this fit to have like a fit of the whole data, and then constrained by the sum. So deriving the sum, and then do a global fit of both. And eventually, hopefully, we can actually reduce the uncertainty on this exotic meson mass, and then understand better what's the origin of this presence of odd wave related to this asymmetry. So that was for COMPASS. And then for GlueX, the situation is very similar, except that it's in practice much more complicated. So in GlueX, there are more complications. So the first one is the beam has a lower energy. Instead of a 190 GeV pion beam, we have only a 9 GeV photon beam. That means that the photon has the time to be absorbed by the target, the proton, to produce deltas and n stars that actually somehow pollute our system, because we are interested only in the dynamics between the two mesons. Of course, what we observe in the detector is like a eta, a pi, and a pion, and then a proton, and then we don't know where those pions come from, pure mesonic interaction, or if the pion, for instance, interact with the proton. So there are some techniques that I'm not going to talk about, either cutting the data or then projecting in different frame, to see that we're going to simply assume that this has been taken care of, and then the remaining data set are only purely mesonic interaction. It's an approximation, and then but we can assume it is done or will be done. So then the question are the same. We need to understand the quantum numbers of this spectrum to actually understand if they are resonance or not. So we saw that quantum number related to the angular distribution, means like what's the angular distribution of eta and pi. The problem in the case of a photon beam compared to a pion beam is that the photon has an helicity. So effectively it doubles the number of partial waves, because for every quantum number in the system eta pi, it can be produced with helicity +1, helicity -1. So the number of waves to extract are double. And in addition, in this case, we also have the scalar wave. We have also the L equals 0 wave, which was not present at COMPAS because of quantum numbers. So because of the number of waves increased, it's actually very difficult and complicated for GluX to directly extract the partial wave. So instead of that, then I develop a formalism, like instead of developing the partial wave of the amplitude, so you know that the intensity is the amplitude square, so it's the probability. So this is like the wave function, and then you square that. So instead of extracting this coefficient that enter quadratically in the intensity, it's actually easier to do a partial wave, like an expansion in YLM of the intensity itself. So there are more waves, as I said, but the good thing is that because the beam can be polarized, we have more information. So of course, more wave comes from the helicity of the beam, but because the beam has an helicity, we can build more observables, like polarized observables. And because we know that it's linearly polarized, we know actually the dependence in the polarization angle, which is capital phi, which is the angle between the electric field of the photon and then the reaction plane. So we can decompose the intensity into a sum of, we can make explicit the phi, the capital phi dependence. And then every term here, I0, I1, I2 can be expanded into spherical harmonic. So we can invert that, and then we can multiply the intensity by YLM, and then we obtain what we call moment. So at least the moment, they don't have well-defined quantum numbers in the data system, but they can be extracted unambiguously, which is a big advantage. And they are quadratic in partial wave, but those relations are known. So instead of extracting the S, the P, the D wave independently, because this, we can show that there are ambiguities, and then it's actually very difficult because of the number of waves. It's actually easier to extract moment and then fit the moment with some model. So this is ongoing. GluX is actually doing that. But so to illustrate this moment, I built like a very naive model. It's just for the purpose of illustration. So this model has like the main resonance that we expect, like the A0, the A2, the A2 prime. And then there are two models, one without any exotic, like without P wave, and one with the P wave, just to see if we can test on each moment, on this toy model, the sensibility of the moment. So you can see that some moment, according to this very naive model, which is probably would be far from the truth, but some moments maybe are a bit sensitive to the pi 1. But it's not ideal. So when I was developing all this formalism for the moment, I was thinking about what kind of observable I can build that is really sensitive to odd wave, like really sensitive to the parity of the wave. So because the beam is polarized, you can build like the beam asymmetry, which is basically the difference versus the sum of where the electric field is perpendicular or parallel to the reaction plane. Now, in practice, if you just do that and integrate over all the decay angle, now this observable does not give you any indication about the wave. But if somehow you bin, or we'll see another technique later, so if you consider that the eta and the pion, they are really in this special kinematics when they actually decay perpendicular to the plane, this beam asymmetry here, because we know that the beam asymmetry actually is like the image of the reflection through the plane. So when the angle are random angle, when you do the reflection through the plane, you don't obtain an eigenvalue, you don't obtain the same system. When the momenta are perpendicular, you see that you obtain the same system up to a permutation of eta and pion, because the momenta are perpendicular, a reflection just switch the two. So in this case, this observable with this special kinematic is actually proportional to the parity of the wave by constriction. So this is very important, because if we can actually measure this, then there will be like odd and even wave would give a different sign for this. Now, of course, this configuration is totally artificial, but because we know all the moment, we know all the angular dependence, we can actually reconstruct this from the known angular dependence. It means that this sigma y is actually an expression in terms of all the moments, all the coefficient of the angular distribution. So the bottom line is that you don't need to wait that you have enough event where the two mesons are perpendicular. You can actually use the whole angular distribution to reconstruct a configuration where the momentum is perpendicular. And so we can see on this toy model what's the effect. So of course, if you don't have any exotic, then in this particular model, you have only one for every wave, because you have only even wave. Now you see that if you add like around 1500, if you add a very small exotic wave here, then you see that you could expect a significant depletion. Of course, there are actually assumptions behind that. And this is probably to exaggerate, but this is to illustrate the fact that this observable might be more appropriate, or at least it's sensitive to the presence of odd wave, that means exotic meson. So this also is currently under extraction with the GluX data. Now, yeah, so just to maybe to finish.
Vincent, you're about 45 minutes through.
Yes, I need 5 more minutes. So here is just to illustrate at the moment that it's very preliminary. By very preliminary, I mean that it's probably totally wrong. But this is just example that the collaboration is working on. And this is also an example of the moment. In this case, it's pi0, so does not have exotic wave, but it's just an illustration of this technique is actually currently implemented in GluX analysis, even in other channel. Yeah, and then in parallel, GluX and with myself and another collaborator, we're actually also in parallel studying the double diffractive region for this reaction. Also, the goal is the same as in COMPASS, is just to understand if we can understand the asymmetry in this case. So here is the beam asymmetry. It's not the forward-backward asymmetry, it's the beam asymmetry. And then the blue is for fast eta, and then the red is for fast pion. You can see that because of isospin symmetry, these two diagrams, the rho and the omega, they are fairly similar. So we expect the blue and the red to be fairly similar, which is what you observe. In the case of the charge reaction, that GluX also measuring, you can actually have like a pion exchange, a charged pion exchange here in the red case that you cannot have in the fast eta. So this fast pion pushes the beam asymmetry toward -1, so that we see that here in this case, the red is actually lower than the blue, and this is what we understand here. So this is illustrated that the fact that in GluX there are a lot of work going on, but unfortunately, it's actually much more challenging because of the spin of the beam, because of the low energy. But in principle, the program is the same. It's really like to fit the low energy, fit the high energy, develop the sum rule to constrain the two, do a global fit, and then extract the property of the exotic mesons. So this is one of the goals of this collaboration, and we participate to that. I think, yeah, so in summary, so we have started this program with COMPASS, which is more clean, higher energy, scalar beam. We actually were surprised by the difficulty we found, like to fit the double diffractive region. As I said, it's more than a year that we're working on that. The program is the same with gluex, or more difficulty. And then before finishing, just like one word on the website that Arnaud mentioned. So years ago, I think, yeah, so 6 years ago, I started this website that is hosted in this. I should change the address, but so this web page, as every time we finish like a project, we make that available for either simulation or downloading. So an example is here. I think these are the SDME, so spin density matrix element for vector meson. So you can choose the vector meson that you produce. You can choose even the energy of the beam. And then if you want, you can even play with the parameter of the model to see the difference. And you can also download the code. So the experimentalists, they download that to compare with their result in their paper or in their talk. And that's facilitate the interaction that we can have like, with experimentalists. And that concludes my talk. So yeah, thank you for your attention.
Thank you very much, Vincent. It was really interesting. I will open now the floor for discussions. If you have any questions, you can either just mute yourselves or raise your hands. No one's going for it. I can ask a question then. I guess about the of course, at the interface of model prediction and experimental data, there is a lot of discussion nowadays about how these things are done. I was wondering if you had any ideas or comments in terms of, say, Bayesian model inference and things like this. Is this something that can be applied already at this stage?
Yeah. So to be honest, I mean, we do develop some tests. In some cases, especially when the data are scarce, we do need to run some confidence tests or Bayesian tests to see which model is better than others. So now, usually, I'm more involved with developing the model, and we have two colleagues like Cesar, Fernandez, typically, and Alessandro. That they are more like they know more. They're more knowledgeable in all these statistical tools. So typically, all these kind of tools, like the lasso, so criteria, if you can get rid of a parameter or not. This is something that they do. So the good thing is that so we really work as a team. So there's two advantages. So if I go back to the one advantage is that several people, they have different expertise. Like as I talk about, like for instance, doing large fit or using a cluster or doing like some statistical tools, but also when we develop models. So the more people we have, the more idea we have about what kind of model we should test. And this goes into the systematic error. So, because of course, so we always test different models. And then just to have an idea about the statistical, the systematic error that you can see here. So the fact that we work in a group, that's also help in actually probing different models. Yeah.
Thank you. Does anybody else have any other questions? I think your talk was too clear, Vincent.
Well, and I will be in Barcelona soon, so if people want to meet, it's not a problem. It will be even easier. So, excuse me, may I ask you? Yes. There is a second P1 Meson, 200 MeV heavier. So have you tried to fit this data with 2 pi1 Mesons? So the thing is, we cannot impose a priori the number of poles. So we we design like K matrix that are fit, and then we try different version for the phase space, different, you know, for the Schumann-Delstam, different degrees in the polynomial in the K matrix. And then we explore we do explore the complex plane. Now we found that, so we found like in general, you find a lot of poles. Now, but most of them, they're actually spurious in the sense that we all the model, there was only one pole, this pi1, that were actually stable and in the region. So I can maybe, let's see if I can, I have other plots. It was this one, determination. So let's see if we have the supplemental material. I don't have it here, the supplemental material. So in the supplemental material, we made a lot of plot when we see the other pole. So every parameterization, so you see the complex plane, you can actually have poles that are very far away. And then we found that if you move a little bit the parameter, those poles, they go even further away. So they are totally spurious. But we found only one stable pole that was actually responsible for these two enhancements. And the reason why here it's shifted is really like the production mechanism. Like in the K matrix, you can multiply the numerator by a polynomial, and then this production, the production mechanism was enough to actually accommodate for this block at 1400 and not at 1600. So only one pole, and more recently, there's another group, I believe it's the Bongacina, but I'm not entirely sure. They did the same analysis, but with much more channels. So they take the compass data, but they also take other experiments, and they found the exact same result as we found. So we're confident that only one pole here for the exotic meson.
Okay, thank you. So the second pole is less reliable, which yes, is mentioned in particle data.
Exactly. It comes from like a very naive fit of this,
okay,
this 1400, yes.
Okay,
there
thank
will
you.
Be the PDG will actually, next time, they will make a difference between Bragg-Wigner fit, like purely on the, and pole extraction. So, so Christoph Anhart is actually responsible for that in the PDG for Meson. So he has started a list of really particles that have been extracted via pole extraction and not naive Bragg-Wigner. So in the next edition of the PDG, it will be more clear, hopefully.
Great, thank you.
Good. Are there any other urgent questions for Vincent? Well, there don't seem to be. So thank you very much, Vincent, for a good talk. Glad to have you in Barcelona soon.
Thank you.
And we reconvene in 2 weeks' time for another seminar, also from an incoming star into Barcelona. So I'll just leave it there with attention so people can join in. All right. Thank you very much.
Thank you, and see you
Cheers.
soon, all of you then.
Thank you.
Thank
Bye.
you.